We're going to finish section, or chapter 5 rather, with section 5.3, which is on what is known as the binomial distribution. The binomial distribution is a formula that allows us to do some problems that would otherwise be quite complicated. We're going to combine a combination along with some rules of probability in order to calculate these rather complicated problems. So before we can use this formula, we have to have a specific type of problem that we're using this on. And the type of problem that we're going to be using this on are probability problems where you can have only two possible outcomes. Now, that seems like it would be rather limited, but in a lot of cases, even though there's more than two outcomes, we can reduce the outcomes to two outcomes. So, for instance, I can say that a die has 6 sides, and I can roll a 1, a 2, a 3, a 4, a 5, or a 6, or I can think of it as what's the probability that I'm going to roll a 2, or the probability that I'm going to not roll a 2. So you can think of it as just two possible outcomes. Either I roll a 2 or I don't roll a 2. So that's been, even though again it started as 6 possible outcomes, we can reduce it to where there's only 2 outcomes of roll a 2, don't roll a 2. So some common examples is, of course, a coin toss. A coin toss has heads or tails. When a baby is born, they are biologically either a boy or a girl. When you roll a die, one that would seem more obviously 2 outcomes, you could think of when you're rolling the die as, is it odd or even? But again, you can reduce a lot of things that don't initially seem like they have only 2 outcomes to those 2 outcomes. So here are all the criteria where we can use the binomial distribution. So we use a binomial distribution when we're trying to calculate the probability from a binomial experiment. And a binomial experiment has to meet all 4 of these requirements. So there has to be a fixed number of trials. So before you start your binomial experiment, which could be, say, flipping a coin, rolling die, what are the chances of getting a certain number of boys or girls out of 5 people or 5 children, but you have to fix the number of trials before you start the experiment. So you can't say, for instance, I'm going to roll the die until I get to a certain number. I'm going to roll the die until I get 3 5s or something like that. When you start, you have to say, I'm going to roll the die 20 times. I'm going to roll the die 100 times. I'm going to flip the coin 50 times. You have to have your number of trials determined before you start. As we mentioned before, you can only have 2 outcomes. Now, there may be more than 2 outcomes if you list everything out individually, like 1, 2, 3, 4, 5, 6, but it has to at least be reduced to 2 outcomes. For instance, I'm looking to roll a 2, so my outcomes are roll a 2, don't roll a 2. If I'm looking at a spinner that, say, maybe has 4 colors, say the 4 colors are red, blue, green, and yellow, then I could say, well, I want to roll, or I want to spin a blue. I want to spin that spinner until so that I get a blue. Well, I then could reduce my outcomes to blue and not blue. Rather than saying there's red, blue, green, and yellow, we can say there's blue, which is this section, and there's all the rest of these are not blue. The next thing is the outcomes of each trial must be independent of each other. So if we're talking about something like a spinner or a die or a coin, we don't have to worry about that because those are all independent. A die does not have a memory. A coin does not have a memory. A spinner does not have a memory, or a roulette wheel. Those things all, quote unquote, reset every time you spin or roll or flip them. If we're talking about cards, then we have to have replacement. So it has to be something like dice, coins, spinner, or you have to have replacement. If we're talking about drawing chips out of a box or balls out of a box, or we're talking about drawing cards, then you need to replace those. So if you're drawing something, then you have to replace it so that they are independent of each other. So each time you start, it resets itself. And because of that, the probability of success must remain the same. So because they're independent of each other, you do get the probability of success remaining the same from trial to trial. So from coin flip to coin flip, or from spin to spin, or from draw to draw, the probability of getting what you want stays the same. So again, if we're saying I want to spin a blue, every time I spin, I have a 1/4 of a chance of getting a blue. The next time I spin, I still have a 1/4 chance of getting blue. The next time I spin, I have a 1/4 chance of getting blue. So we have to remain the same for each trial. If we don't replace, then that's going to change the probabilities on the subsequent drawing. So that's why we have to replace. So when we're talking about this binomial distribution, we're going to see in the formula some things that we haven't, some variables that we haven't seen before. They're similar to some things that we've seen before, but they're not exactly the same. So this first one here, P of S, means probability of success. P of F means the probability of failure. So this little p and this big P of S are both almost the same thing. It's just that this is the symbol for the probability of success, and this is actually the numerical probability of success. So for instance, this might be probability that you roll a 2. This would be P equals 1/6, because you have a 1/6 chance of rolling a 2 on a die. Now, in this case, if I use the same example, P of F is the probability of failure, so that would be the probability of not getting a 2, because our success in that case is rolling a 2, so our failure is not getting a 2. And then our numerical equivalent of that would be 5/6, because if rolling a 2 has a probability of 1/6, then not rolling a 2, which is the complement of it, must have the probability that complements this to add up to 1. So 1 minus 1/6 is 5/6, or 1/6 plus 5/6 equals 1, however you like to think of that. And that's what this says right here, is that 1 minus P has to equal Q. So if I tell you P is 20%, then Q has to be 80%. If I tell you P has to be 3 out of 10, then that means Q has to be 7 out of 10. These two together have to add up to be 1. Let's do another one. So if I tell you P is 17/50ths, then that would mean Q would be the rest of that to add up to 50/50ths, which would be 33. So again, you get this from 1 minus 17/50ths. A lot of times with these we have percentages or decimals, so that's kind of nice. So say P is 0.81, then Q would be 0.2, whoops, sorry, not 0.29, 0.19. And again, the two together have to total up to 1. So 81% or 0.81 and 19% or 0.19 add up to a total of 1.00. N we have seen a lot. That's just the total number of trials. Sometimes we use it as the number in the sample, but in this case the trials are like the samples, so it really does fit in. So N is the number of trials. So the number of flips or rolls or selections. You can do any number of things with binomial distributions, so it could be any number of things that are defined. And then the number of successes is the number of times you get what you're looking for. One of the things that you have to remember or understand with a binomial distribution is that the number of successes are not necessarily positive. A success in a binomial distribution could be, say, you're looking to see how many people, or what are the chances that you'll get 3 out of 10 people have had a family member diagnosed with cancer. Well, having a family member that's diagnosed with cancer is definitely not a success. So, or is definitely not in the typical sense of the word a success. But because it's what we're looking for in the trial, someone who has had a family member with cancer would be a success. So you can't think of success as being like a positive attribute or a negative attribute. It's just simply what you're looking at, what you're studying, what you are trying to find. And then, of course, since X is the number of successes out of N trials, you can't have X be larger than N. So if N is 6, then your number of successes could be, well, I want no successes out of 6, 1 success, 2 successes, 3, 4, 5, or 6. You can't go any more than 6 successes out of 6. And so that's your highest you can go. And then, of course, having no successes is the lowest you can go. So this is the rather, at first glance, intimidating formula for the binomial distribution. Again, though, this is very, very helpful, and I'll show you when we see one of the actual problems what you would have to do without the binomial distribution. But this is the formula for it. And you'll notice that in this part of the formula we have N, which is the number of trials. We have another N, same number. And then we have X's, which would be the number of successes. We also have P, which is the probability of success. Q, which is the probability of failure. So this number plus this number together have to add to 1. And then we have X and N minus X. These two, again, these two together have to add up to be N, because you have the number of successes, then N minus X would be the number of failures. So the number of successes and the number of failures together have to total the total number of trials. Now, another thing, you can't change this on the card. This is not going to be on the card this way, but if you can remember that this right here is the exact formula for a combination. So it would be an N choose X, and you can do this on your calculator. So we can think of this formula as P of X equals N choose X, or N combination of X, P to the X, Q to the N minus X. Makes it seem a lot less intimidating if you replace that messy part here with an NCX, especially knowing that you can do an NCX very quickly and easily on your calculator. So we're going to see our first example of what a binomial distribution type of problem looks like. So again, with a binomial distribution, you have to have fixed number of trials. Let me rewrite this. So you have to have a fixed number of trials. You have to have a desired number of successes. I might be saying this a little different than what we said before, but it's the same things. And you have to have the probability between each trial or each part of the experiment has to remain the same. So let's see if we can get that to fit with what we're looking at here. So a survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. 10 people are selected at random. Find the probability that exactly 3 will have visited a doctor. So this is a great example of the success of this experiment or this survey is visiting a doctor. Most of us wouldn't really consider having to go to the doctor sometime in the past month as necessarily being a success. But for this, because that's what we're looking at, that's our success. So visiting a doctor is considered our success. And we have a desired number of successes. So we want exactly 3 successes. We want 3 people to have visited the doctor in the last month. That's out of a fixed number of trials. So 10 people, that's our N. That's our fixed number of trials. That's our N. And they were kind of a little vague with our probability here because they wrote it out in words. But 1 out of 5, that's our probability of a success, or our P is 1 in 5. So while we're talking about that, let's go ahead and do the probability of our failure. That's called our Q. If our probability of success is 1/5, then our probability of a failure is 4/5. These two together have to be 100 because that's the only two things that can happen. Either you have a success or you have a failure. So now let's write out the formula. So we're looking for the probability that we have exactly 3 successes out of our 10 trials, and that will be equal to, remember, actually let me just write out the general formula first instead of filling in the numbers. So probability of X successes equals N choose X, P to the X, Q to the N minus X. So let's fill that in now. So the probability of exactly 3 successes in this experiment, our N is the 10 people. We want to do a combination of that with 3 because we want 3 successes. So 10 total trials, we want 3 successes. Now P and Q are going to be our probabilities. So the probability of a success is 1/5. The probability of a failure is 4/5. I know we haven't filled in the powers, but because the P and the Q go together, I almost always will write those down, the 2 bases down before I do the powers. So probability of success, 1/5. Probability of failure, which is the Q, is 4/5. X is the same as this X. So how many successes? A probability of 1/5 success, 1/5 probability of a success, and we want 3 of them. Probability of each trial having a probability of failure is 4/5, and if we want 3 successes, that leaves 7 failures. So again, this is 3 successes, 7 failures, and this has to total N, which equals 10. So if I have 3 successes, I have 7 failures. And then it's just a matter of typing this in your calculator. So you type in 10 choose 3, which comes out to be 120. And then you multiply that times 1/5 to the third. And we don't need any of this as intermediate steps. I mean, I didn't even really have to do that. But just so you know that you're typing this in correctly, 10 choose 3 should come out to be 120. And then you times that times the fraction 1/5 to the third power. Bring it down, do a multiplication, fraction 4/5 to a power of 7. If you do that correctly, you should get a total of 0.201. So just slightly over 20%. So again, what we're saying here is that if we pick 10 people with this probability set at 1 out of 5, 10 people, we have a 20% chance, or a little bit better than 20% chance, that exactly 3 of those 10 people will have visited a doctor in the last month. Now, what is so special about this formula? Well, if we didn't do it this way, we would have to figure out the probability of all of the different ways that this could happen separately. Having exactly 3 out of 10 could happen in 120 different ways. That's what this 120 represents. So we would have to compute what if the first person visited a doctor, the second person visited a doctor, the third person visited a doctor, and then nobody else did. So what is that? 6, 7, 8, 9, 10. And then we would have to do this where the D's could be in any spot. So we could do D, D, N, D, and then the rest N's. We could do D, D, N, and D, and the rest N's. And that's still keeping the first 2 D's and only moving the third D. We would have to do all the different ways that you could have the 3 D's in any position. After you did that, you would have to do 4 D's. I'm sorry, not on this one you would not. I take that back. But you would have to do all the different ways that you could have these 3 D's somewhere in this order. And it just so happens that that is a 10 choose 3, which would be 120 different ways. But everything else remains the same. So even though they're in different places, you would still have 1/5 3 times, and you would still have 4/5 7 times if you multiply these out. Like, for instance, the first one would be 1/5 times 1/5 times 1/5 times 4/5 times 4/5 times 4/5. This would have to be 10 of these. So we're up to 6, 7, 8, 9, 10. So the next time, the 1/5 would get swapped with one of the 4/5, but we would still have 3 1/5 and 7 4/5. So again, 3 1/5 and 7 products of 4/5 we would multiply, but we have 120 different ways to do that. Now, you don't have to remember it that deeply every time you do the problem, but that's where that all comes from. So if you can remember on your formula sheet that the P of X equals n factorial over n minus x factorial times x factorial, and then P to the X, Q to the n minus x, if you can get this all filled in, if you can recognize it as a binomial problem and get all the little bits filled in, you have it. And one of the easiest ways to get it filled in is to remember that this is an n choose x. So let's do another example. So our next problem says a survey from Teenage Research Unlimited in Northbrook, Illinois, found that 30% of teenage consumers receive their spending money from part-time jobs. So the other 70% either don't have spending money or they get their spending money from their parents. We don't know, but 30% from jobs, 70% not from jobs. So receiving their spending money from a job, that's your success. Those are the students that you're looking for, are the ones that receive their spending money from their part-time jobs. So let's look at our formula. Again, P of X equals N choose X, P to the X, Q to the N minus X. So let's write everything out. So our N is how many students we're going to select. It's teenagers. Our P is 30%, which leaves our Q as 70%. So the probability each time you pick a teenager that they will have received their spending money from a part-time job is 30%, and then the chance that your randomly picked teenager is going to get their spending money from somewhere else or not have spending money is going to be 70%. Now the X is a little bit tricky because this says at least 3. At least 3 means that our X is going to be 3 and 4 and 5. In other words, we're going to have to figure out the probability of exactly 3 out of the 5 having a part-time job, plus the probability that 4 get their spending money from their part-time job, and then plus the probability that 5. So the probability that we get 3 out of the 5, 4 out of the 5, and 5 out of the 5, because it says at least 3. So that requires us to actually do 3 separate calculations and add them together. Now, as a note, you will see this in your homework on the test for chapter 4, 5, 6. I will not have you do one that has multiple ones like this. I'll just give you a single binomial problem like we saw in the last one. So I'll just give you one of these. So I would say, what's the probability that exactly 3 of them, or exactly 2 of them, or exactly 5 of them? I won't do 3 or more, or 2 or less, although you might see this on your homework. Okay, so let's calculate each of these separately so that we can add it up. So the probability that exactly 3 out of the 5 have a part-time job, remember we're going to do NCX, so our N is 5, and in this case our X is 3. So 5 choose 3. Our P is that 30%. Okay, so we're going to take that times 30%. Let me put a parenthesis around this. To the power of, again in this case it's 3. We want 3 successes in this one, which leaves a 70% chance for our 7 failures. I'm sorry, that's not 7. We only have a total of 5, so our Q is actually 2. Or not our Q, but our N minus X is 2. Because these two together have to add up to 5. So this is the number of successes, and this is the number of failures. So in this case, the probability that we get exactly 3 successes means we would have 2 failures because we're picking 5 total. So if you multiply this all out, you should get, hold on, I've got it written down over here. You should get 0.132. So this comes out to be, go ahead and calculate that on your calculator and make sure that you're getting that. You should get 0.132. So that's going to be this number, 0.132. Then we're going to add that to the probability of 4. So we have to calculate the probability of getting exactly 4 out of the 5 that had part-time jobs. So 5 choose 4 this time. My probability is still 30% for a success and 70% for a failure. But this time I want 4 successes, which leaves only 1 failure. If you multiply out 5 choose 4 times 0.3 to the 4th times 0.7 to the 1st, you should get 0.028, or about 2.8% chance that you're going to get 4 out of the 5 that have part-time jobs. And then last but not least, the probability of 5. Oh, and let's put this back up here. So that's our second one that we're going to add. And then P of 5 is 5 choose 5. We want all 5 out of the 5 to have a part-time job. So that leaves 0.3 to the 5th, 0.7 to the 0. 0.3 and 0.7 remain the same. That's our 30% and 70% success and failure rates. But in this case, since we want 5 successes, that means that we don't have any failures. So we want every student that we pick to have a part-time job. If you multiply this out, this comes out to be about 0.002. And what's kind of interesting is 5 choose 5 is actually 1. 0.70 to the 0 is 1. So the only thing that we're really multiplying here is the 0.3 to the 5th, and that comes out to be 0.002. Again, you don't have to realize that as you're typing it in. Your calculator will handle it, but alright, so if we add those all up, that comes out to be 0.162. So you only have a 16.2% chance that 3 or more of the students out of 5 have a part-time job. Or that's where they earn their money from, I should say. So on this next problem, it directs you to use table B to work this problem out. And you can use the table on the problems in the homework that say use table B, but you can also use the formula. In fact, I would probably prefer that you use the formula. If you want to double check it with the table, you can. But the table is kind of an old-fashioned method for doing the binomial distribution. It was used at a time when we didn't have calculators to be able to do the combinations so easily, and we didn't have, we just didn't have the technology that we have, and so this table was developed in order to be able to do these calculations. So I'm going to show you how to do this one with the formula, and then I'll show you how to use it on table B, just as kind of a, if nothing else, kind of a curiosity. But again, don't worry about being able to use table B. Wouldn't ask you to do that on the test, and if you run across one on the homework, the Connect Math has no idea whether you used the formula or you used table B. So just use whichever one you would prefer. Okay, so a coin is tossed 3 times. Find the probability of getting exactly 2 heads. So let's fill in everything that we need. So n is 3 because we're tossing it 3 times. Our x is 2 because we want exactly 2 heads. So our success is flipping a heads, and we want to get that twice. Our probability of success is 0.5, or 50%, or 1/2, because getting a heads on each flip, each time that's 50% chance. And on each flip, you have a 50% chance of failure. So 50-50, heads, tails, success, failure. So if we want to calculate the probability of getting exactly 2 heads, we would do a 3 choose 2. Our P would be 0.5. Our Q would also be 0.5. We want 2 successes, which leaves 1 failure. Remember, this number and this number together have to total this number. And then this number right here is the same as this number. So 3 choose 2, and then the 2 is the same, and then the 2 and the 1 together have to be the total number of flips or trials. So if you multiply that out, 3 choose 2 is actually only 3. And then we're going to multiply that times, again, 0.5 squared times 0.5 to the first. So 3 times 0.5 squared times 0.5 to the first, you get an answer of 0.375. So 37.5% of the time, you should get exactly 2 heads and 1 tail. In the long run, or the expected value, the expected number of times is 37.5% of the time you'd get 2 heads and a tail. Now, if you want to use the table, again, it's called Table B. It's in the appendix in the back of the book. And let me show you how to use that. I'm not sure if my pen, no, my pen will not write on here. Okay, so we're going to go off of what we had. We had our P is listed up here at the top. Your N is here, your X is here. So in this case, our N is 3. Okay, let me see if I can highlight that. I'm going to try to highlight our things here. So we're going to highlight, we've got N of 3. I'm not sure it's going to let me do that. All right, we'll just have to follow along. N of 3, X of 2, because we had 3 trials, 2 successes, and then we follow over to our P of 0.5. See how it's up above here? And so this is our number for our probability of that happening. Now that seems all great, and you're like, well, that's quicker than doing it on my calculator. The problem is, you'll notice that the P's, you can't list every possible probability. So they start with 5%, and then they go to 10%, 20%, 25%, and then they just go by tens, 30, 40, 50, 60, 70. So if you have anything that's in between, you have to kind of make an estimate of the value that would be in between, or you just have to go to the closest one. So say you had P of 31%, you'd have to estimate it with P of 30%. So it's not as exact. The other thing is, this gets really big really fast. When you have only 3 coin flips, the most successes you can have is 3. But if you go down here, you'll notice if you have 11 coin flips, you could have up to 11 successes, anywhere from 0 to 11. So you need 11 rows, actually 12 rows if you count the 0. You need 12 rows for an N of 11. And it gets really big really fast. So this takes up several pages, and it only goes up to 20. So it goes from page, that's 647 is the end of it. It only starts on 642, so it takes 5 pages just to get up to an N of 20. So even though it's kind of, in some ways it might be quicker if everything is perfect, it has a lot of limitations to being able to use it. Again, go ahead and use it on the homework if you'd like to, but you can just as well use the formula. In fact, probably be better to practice the formula. So the last thing that we need to cover in with the binomial distribution, in fact, the last thing we need to cover for Chapter 5 for all the probability distributions is how to find the mean and the variance for a binomial distribution. Remember, again, this is for the specific case where you have only successes and failures. You have a fixed number of trials, a fixed number of successes, and you have independent trials. So each trial remains the same probability from trial to trial of success. The formulas are actually very simplistic. In order to get the mean, all you're going to do is you're going to take the number of trials and take it times the probability of a success, and that will get you your mean. Then to get the variance, you're just going to add one thing. You're going to take the probability, or the number of trials, times the probability of success times the probability of failure. That's going to get you your variance. And just as always, once you have the variance, all you have to do is take the square root to get the standard deviation. Let me write this down. So n is number of trials and then you're going to take that times the probability of success on each trial. And then here you're going to do the number of trials times the probability of success, and then you're going to multiply that times the probability of failure, and these two together have to total 1 if you add them up. And then to get the standard deviation, you just do the square root. So let's give that a shot, and then we will be done with chapter 5. Again, remember, this is not something that you have to memorize the formula. You just have to recognize that this is a binomial problem, and they're asking you for the mean, and then you're going to go to chapter 5 on your card, on your formula card, and you're going to look for mean of a binomial distribution. So the mean is n times p. So let's look at the situation. The statistical bulletin published by Metropolitan Life reported that 2% of all American births result in twins. Now, that doesn't mean 2% of people are twins. It means 2% of the births. So, for instance, on average, if there were 100 births, there would be, out of those 100 births, there'd be 2 pairs of twins. So there would be 4 babies that were twins, but 2 pairs because they're considered one birth. So if a random sample of 8,000 births is taken, find the mean, the variance, and the standard deviation. So let's write everything out. The mean is n times p. The variance is n times p times q. The standard deviation is the square root of n times p times q. So in this case, n is 8,000. The p is 2%. And then be really careful with the q. Sometimes when that p is really small, people will mess up the q. So it's not 20%, it's only 2%. So q is 0.98. 98% and 2% would be 100%. So be cautious not to assume that this is 20% and then write q as 0.8 or even 0.08. You have to make sure that these two total to 1. So let's calculate. The mean is n times p, so that would be 8,000 times 0.02. So out of 8,000 births, you would expect 2% of them to be twins, and that comes out to be 160. So 160 births out of 8,000 would be a set of twins. Now if we want to do the variance, all we do is the same calculation, 8,000 times, fix that a little bit, it kind of wrote on top of itself here, 8,000 times 0.02 times the q, which is 0.98. And if you enter that in right, that comes out to be exactly 157. So that's the variance, and then the standard deviation is the square root of 157, which is approximately 12.5. And it tells us, I don't think it tells us, but what the book did is this, it rounded these to the nearest whole. This one actually came out to be 156.8. And I'm not sure why they rounded these to the whole. I guess maybe because they're thinking you can't have part of a birth, but variance and standard deviation don't necessarily need to be a possible or a potential number. So I think it would be okay to write it 156.8 and 12.5 but they actually wrote it as 157 and 13. So just watch what what Connect Math asks you to write it as. And that's all we have for Chapter 5.